Off with looking at the different definitions of acids and bases. We looked at the Arrhenius definition, which looked at how an acid or a base behaves in water. Then we looked at Bronsted-Lowry, which looked at proton transfer, removing a hydrogen versus adding a hydrogen. There is one more definition, and this is the one that organic chemists use because organic chemists look at the movement of electrons. So molecules as Lewis acids and Lewis bases. An acid is anything that can accept a pair of electrons. So it's an electron pair acceptor, so something with a positive charge. Okay, so like an H plus, that could accept electrons. All right. A base is anything that has electrons to donate. A lone pair, a negative charge with extra pairs on it. Okay, so if we look at a reaction, now the first thing I want to point out, the arrows always go from the electrons to where they're going, never the other way. It's always from the electron rich to the electron poor, always from the Lewis base to the Lewis acid. But look at this thing here. Okay, we got a boron trifluoride. It doesn't have a hydrogen, so it's not a classical acid. It doesn't have a proton to donate because it doesn't have the hydrogen. So it's not a Bronsted-Lowry acid. Yet it still could be classified as an acid under Lewis definitions because it can accept a pair of electrons and make a coordinate covalent bond with the nitrogen. And if you don't remember the definition, a coordinate covalent bond is a bond where instead of one electron coming from here and one coming from here, something donates both electrons to bond with it. We call the product an addict, and that's our product. Okay, so it says identify the Lewis acids and bases in the following reactions. All right. Well, I'm looking for electron rich and I'm looking for electron poor. So we got electron rich, that must mean I'm the donor, I'm a base, they use blue for base, and red for the acceptor. Let's look at the next one. Letter B. Letter B, electron rich, electron poor, donor, base, acceptor, acid. Here, electron poor, positive charge. This must be my electron rich. Yes, it is. It's water, has a lone pair on it. And here's where and why it's called Lewis. It's because your Lewis structures become important here, looking at lone pairs of electrons. So, in that H2SO4 example I showed in the homework during the live video there, the SO4 has a lone pair on it and a double bond, so it's electron rich, so therefore it could donate it, so it would fall under a Lewis base. Okay, also. All right, okay. So that leads us to what this slide is showing here. If I have a beaker of water, okay, and I add water to it, and I said to you, what is the product of this reaction of taking a beaker of water and adding more water to it? You would rightfully say, well, you have water. And you have a lot more of water. And you're technically right, but. We have to go back to Bronsted-Lowry definition, where we talked about water being amphoteric. Where water, in the presence of an acid, okay, could make hydronium, and water in the presence of a base makes hydroxide. Now for completeness, we'll put that there, and we'll put this here. So here, water's acting like a base. And here, water's acting like an acid. Okay? Well, up here, what's to say that water doesn't act like a base and an acid when it's with itself? What's not to say that this water right here acts like an acid, and this here acts like a base? They do it down here, so why won't they do it together? And the thing is, they do. They do it at a very, very low concentration. But actually, if you have a glass of water, inside that glass of water exists water as the majority of the thing, but in very small quantities, there's H3O plus and OH minus. Now again, it's very small quantities. Okay? We call this the autoionization of water because water can act like an acid or a base in the presence of an acid or a base. How much of this I create is all dependent on what I'm reacting with the water. In our case, we're reacting just water with water, and we get out some hydronium, a very small amount, and a very small amount of hydroxide. So inside your beaker or glass of water right now, okay, exists some hydroxide and some hydronium. Now, if I were to write a Kc for this expression, the Kc would be equal to the concentration of water squared on the bottom with the concentration of H3O plus on top and the concentration of OH minus on top. The thing is, just like our strong acids, or for that matter, doing our Ka, this value is so large that it remains unchanged. Okay, so we get rid of Kc, and what we call it is the Kw, the constant due to water, or, again, the autoionization of water, which would then equal the concentration of H3O plus times the concentration of OH minus. In water, okay, this value is equal to 1.0 times 10 to the negative 14th. That is a constant, which means in water, the concentration of H3O plus is 1.0 times 10 to the minus 7th, and that's why I said very, very small. And the concentration of OH minus then, if we do the math, has to also be 1.0 times 10 to the negative 7th. Okay. Now again, this is temperature dependent. This is at room temperature, but that is our Kw value. So what? Who cares that water does this? Well, it's important because all of our solutions are made in water. Which means that if I make up an acid solution, yes, the majority is going to be H3O plus, but just based on the fact that water self-ionizes, there should be some OH minus in there. That if I make up a base, yes, I should have a lot of OH minus, but there's going to be some H3O plus in there because water self-ionizes. Okay. questions on this before I move on? Because this is going to be important for the calculations we're doing today. I'm going to rewrite that up here. Kw equals the concentration of H3O plus times the concentration of OH minus. Kw always equals 1.0 times 10 to the negative 14th. All right, any questions? We good? So, if I compare my values of H3O plus to OH minus, if I was only given those, and I wanted to know, am I an acidic solution, a basic solution, or a neutral solution? If I have more H3O plus, okay, then OH minus, I'm acidic. Okay. If I have H3O plus equal to OH minus, I'm a neutral solution. And if H3O plus concentration is less than OH minus, I am a basic solution. Okay. So if I were given values and said something like H3O plus is 1.0 times 10 to the negative second, and OH minus is 1.0 times 10 to the negative 12th, am I a basic, an acidic, or a neutral solution? If this was 1.0 times 10 to the minus second, and this is 1.0 times 10 to the minus 12th, this is greater than this, so I'd be acidic. If it was the reverse, and this was the times 10 to the negative second, and this was times 10 to the negative 12th, then I would be a basic solution. If I was given just one of these and I wanted to know the other one, I would plug it into this formula. So this formula is important. So if you're actually taking notes, all right, while I'm doing these lectures, this formula is important because if I'm given H3O plus, I could find OH minus using the Kw value. Now I'm going to show you another way to do it based on a little math trick, but for right now, that's the way to do it. And in the slide, sample problem 18.2 looks at something like that, so you could try that one for homework. Okay. And I'll give you more on it. So if I'm given one, I could plug it into here. This value never changes, and find the other and then compare. Questions? I'm going to leave this up here. All right, then that leads us to a term called pH. Okay. pH essentially tells me how acidic I am. Anything with a, and I'm going to make that P a little bit smaller, just because. Anything with that little p in front of it means the negative log of a value. Okay. So what this really means is the negative log of H plus that we make. And really, it means the negative log of H3O plus that we make. So if I'm given a concentration of H3O plus, if I take the negative log of that value, okay, if I take the negative log of that value, yes. Yes, yes, yes. Okay. Of whatever that value is, I will have the pH. Well, we all learned the pH scale at some point in time. Okay, where 7 is neutral. Okay, so we're going to call this the pH scale. That below 7 is acidic, and above 7 is basic. Now, I know they told you 1 to 14, but the math shows that it could actually go 0 to 15. Okay? So neutral 7, basic's anything above it, acidic is anything below it. Why is that the case? Well, if I'm an acid, I should have a lot of H3O plus. If I'm a base, I should have very little H3O plus because I'm a base. That's not what a base does. If I take the negative log of a big number, my answer is smaller. If I take the negative log of a small number, my answer is bigger. So a base would have a low H3O plus value. Okay. Take the negative log, I should get a bigger number. An acid should have a large H3O plus number. Take it, and I should get a low value. Base 10. Log base 10. Now, there's a totally other scale besides the pH scale. There's also, and no one ever talks about it, but there's also a pOH scale, which essentially is the negative log of OH minus. Okay. Now the pOH scale, 7 is still neutral, but it runs opposite. Anything below 7 on the pOH scale is basic, and anything above is acidic for kind of the same reason the pH scale runs. If I'm an acid, I should have a low amount of OH minus, and if I'm a base, I should have a high amount of OH minus, and we follow our negative log rules. Negative log of a small gives me a bigger number. Negative log of a large number gives me a smaller number. Okay. So two scales based off of the negative log, and depending on your calculator, you either put the negative log in first and then put the number, you hit number, log, negative. However you have to do it, you should figure it out. All right, questions on pH and pOH. So why is 7 neutral? Well, that goes back to this. This is to the minus 7th, this is to the minus 7th, and that ends up being our 7 neutral. Why is our pH scale, they tell us 1 to 14? Okay. It really goes 0 to 15, but that's where our numbers are coming from in our scales. The 7s, the 14s. So let's take a look at a problem. Okay. Now, in order to do these problems, it's important to distinguish. Do I have a strong acid? Do I have a strong base? Do I have a weak acid? Do I have a weak base? Right now, we're going to deal with strong acids and strong bases. If I have a strong acid or base, the molarity of the strong acid or base tells me the concentration of H3O plus for an acid or OH minus for the base. Because I completely dissociate. Okay. So, if I were given a problem that said I have 1 molar nitric acid, and I want to know the pH, the pOH, the concentration of H3O plus, and the concentration of OH minus. I could do that given just this information. First of all, I'm a strong acid. The way I know I'm a strong acid, I have 2 or more oxygen than hydrogen. So go back to our acid-base review. So, since I'm a strong acid, my concentration of H3O plus is 1 molar. Because a strong acid, the molarity tells me the concentration of H3O plus. Okay? Now, let's find the rest. Well, if I want to know the pH, I need to do the negative log of the H3O plus. So I need to take the negative log of 1. Okay? And if you take the log of 1, what do you get? What's the log of 1? Or for that matter, the negative log. Without even putting it in our calculator, what's the log of 1? 0. Right, Taylor? Yep. So, the pH, we're already showing by math that pH scale that they teach you in high school and in biology class of 1 to 14, the math actually predicts it can go lower. So my pH is 0. Okay, well to find the pOH, I need the negative log of OH minus. I also need the concentration of OH minus. Okay? So, to find the concentration of OH minus, I come up here and use this formula. 1.0 times 10 to the negative 14th equals the concentration of H3O plus, 1, times the concentration of OH minus, I don't know. So, I find out that it is 10, or 1.0, sorry, times 10 to the minus 14th if I do the math up there. Take the negative log of 1.0 times 10 to the negative 14th, and you get 14. And basically, we've solved the problem and figured out what's my concentration of pH. I will have some pOH because water dissociates in itself. I know the H3O plus, I know the OH minus, and you could always double check your answer if you understand the ranking. My pH should be a very low number because I'm an acid. My pOH should be a very high number because I'm an acid. Okay. Let's try another one. Let's do another acid. Okay. Let's say I have 0.35 molar H2, let's do HClO3, chloric acid. Okay, and I want to know the same things. I want to know the pH, I want to know the pOH, I want to know the concentration of hydronium, I want to know the concentration of hydroxide. Okay, first thing I do is I look at it, I say it's an acid. I know it's an acid, it has a hydrogen to donate, and I know it's strong. It has a difference of 2 or more oxygen to hydrogen, so 3 minus 1. So, since it's a strong acid, the concentration of the acid is my concentration of H3O plus. I want to find the pH. I'm going to take the negative log of that concentration, 0.35. Okay. 0.35. Clear. Log. Clear. 0.35 log. And I get the negative log of, the answer is, I'm getting 0.456. 0.456. Okay? For the pH. My OH minus, okay? I can figure out my OH minus by using the kW. All right? So I plug in, I have 1.0 times 10 to the negative 14th equals the 0.35 times whatever my OH minus is going to be. Okay, so we figure that out. We take one, there's my exponent, 14 negative, divided by 0.35. I get 2.86 times 10 to the negative 14th. And if I take the log of that number, the log of my OH minus that I calculated, okay, I get 13.54, give or take. 544. We'll go out to 3 decimal places. Okay? Questions on that? Oh, negative log, negative log. I forgot the negative. Always negative log. P always means negative. Now, I want to point something out that'll make the math a little bit easier for you, in case you don't notice it. And here's where that 14 and everything comes into play. Now, you do it this way, you're going to get it right every time, but using a couple math tricks and negative logs and things like that, adding your pH and your pOH together should always equal 14. And that's why I took it out another thing, so you could see that it does equal 14. If I add these together, they should equal 14. So if I know one, I know the other. Like, as soon as we found this, I didn't need to do the negative log of OH minus. I could have took 14 minus this and still got the same answer. So, a little side note here. Now, your books don't tell you this because they assume you understand the math. But pH plus pOH should equal 14. So if you look at the last one that we did with nitric acid's pH was 0, the pOH was 14. The other thing I want to point out is that you really don't need to do this to find OH minus. This will work if I know the pH or the pOH. The concentration of H3O plus could be found by doing the reverse of this. And this is, Taylor, when you asked, is it the power of 10? Yes. H3O plus is equal to 10 to the minus pH value. Now this gives you a rough answer. It's not exact, but it gives you pretty darn close. Concentration of OH minus is equal to 10 to the minus pOH. Okay, so these are just remanipulating or understanding powers of 10 to figure it out a little bit easier. Oh, it could. You could end up with a -1. You could end up with a -1 pH. So what's the log of 10? So what if my molarity was 10? If I had a 10 molar solution. What's the negative log of 10? Exactly. So there it is right there, -1. And if we're going to get really into it, so for instance, concentrated sulfuric acid that you use in a lab, okay? Concentrated sulfuric acid, if you use that in the lab, all right? So concentrated sulfuric acid, all right, has a molarity of 18.4. Concentrated nitric acid is 15.8. Okay? I wanted to get the exact. I always remember it as 16, but I knew it's not 16. It's 15.8. So if we take, and it's a strong acid, if I take the log of 15.8, the pH actually ends up being -1.2-ish. So the pH of this is actually -1.2, which means its pOH is really what? 15.2? So yeah, that 1 through 14 scale, the math will tell you a little bit different when you get into your concentrated stuff. All right, let's do a base. Let's say I have 2 molar sodium hydroxide. And I want to know the same values again. I want to know the pH. I want to know the pOH. I want to know the concentration of H3O+. I want to know the concentration of OH-. Well, since I'm a base, and I'm a strong base, whatever my concentration is my concentration this time of hydroxide. Okay? Now I can find my pOH, which is the negative log of 2, which ends up being 0.301. .301. Actually ends up being -0.301. 2 log negative. Yep, -0.301. Now, I could do it the long way and plug everything in up here. Or I could do it the shortcut way and you could check my answers. But 14 minus this value tells me that the pH should be 14.0 301. And if I take 10 to the negative I get 5 times 10 to the negative 15th. So all I did here was this trick here, to find this answer. And I used this trick over here, 10 to the minus pH, and got that value. But if you take 1.0 times 10 to the negative 14th, exponent, there it is, negative 14, and you divide it by 2, your answer should still be the same, and it is 5 times 10 to the negative 15. So both ways are acceptable. Your book is going to show you this way and the negative log way, because that's going to be right every time. But if you understand your powers and how they work, you can use these too. They don't tell you that, but it works out every time. You might be off by a decimal place, but it helps out. All right, questions on this. How to find pH, pOH, H3O plus, OH minus. This is for strong acids and strong bases. Nothing? Bueller? So what about weak acids? Good question. Tune in Thursday for weak acids. And what I'll tell you is review Icebox from Chapter 14. Because weak acids don't completely dissociate in water. Since they don't completely dissociate in water, looking at their molarity won't do much for us. Okay? Looking at their molarity won't do much, and I can't assume that if I have 2 molar of a weak acid that I'm going to get 2 molar H3O plus, because I don't completely break down. Okay. So that being said, homework. From the slides, sample problem 18.2 and 18.3. Page 835. (18.23 to 18.30). And then on 838, Lewis acids, Lewis bases. (18.138 to 145). Okay, so there's the homework. And that's Lewis acids and pH and pOH.